Hello, good afternoon, students. I am Nishu. Hope all of you are fine. Now, in this time of lockdown, I don't want to lack your studies, so I am trying my best to teach you online on my YouTube channel. Now, we have to start the next topic, linear transformation. As we discussed already the vector spaces, a mapping T from vector space V to another vector space W is said to be a linear transformation if and only if it satisfies the two properties, that is T of V plus W gives you TV plus TW for all VW belongs to V. Second, T of AV is equals to ATV for all V belongs to V, where V and W are the elements of vector space V and A is a scalar which is a constant or any scalar which belongs to the field F. First property is known as the additive property of linear transformation and second property is known as the homogeneous property of linear transformation. Now, since linear transformation is a mapping from vector space V to vector space W, if it defines a mapping from the same vector space V to same vector space V, then it is known as, this linear transformation is known as linear operator. Linear functional, linear transformation T from the vector space V to the field F is known as linear functional. As we had discussed, any linear mapping T is said to be linear transformation if it satisfies two properties. We had already discussed the proof of the theorem, which is very important, that is, any linear transformation T from vector space V to vector space W is said to be linear transformation if and only if it satisfies this property. That is, T of alpha V plus beta W gives you alpha of TV plus beta of TW, where TV and TW are the elements of range, alpha and beta are any scalars. Students, you can easily verify this property is a combination of first two properties, that is the property of addition and property of homogeneous property over T. Now, because it contains addition of two elements and the scalar multiplication of two elements. Now, questions based on this topic. Question 1. One thing more, if you have to only show that this mapping is a linear transformation, then you can use this property. But if you have to check whether the given linear transformation is or not, then you have to satisfy these two properties. Okay. Now, question 1. Show that given is linear transformation. We have to show, that is T V3R to V2R defined by T of x, y, z, x minus y plus z to 2x. Now, students, clearly any element of domain is of 3 tuple, that is x, y, z, and range should be of 2 tuple, that is x minus y plus z, one element, 2x is your second element. That means this belongs to V2R and this belongs to V3R. Clearly, now we have to show this is a linear transformation. Solution. First of all, to show linear transformation, we have to satisfy this property, that is T of alpha U V plus beta W. That means first of all we have to take any V and W, that is two elements, belongs to V3R. Let U x1, y1, z1 because it belongs to V3. That means it consists of 3 tuple, and V x2, y2, z2 belongs to V3R. Then take left hand side, that is alpha u plus beta v, that is alpha of x1, y1, z1 plus beta of x2, y2, z2. This gives you a simple multiplication, scalar multiplication, alpha x1 plus beta x2, alpha y1 plus beta y2, alpha z1 plus beta of z2. Now clearly 3 elements, this belongs to V3R. Now take left hand side of theorem first, that is T of alpha u plus beta v. This gives you T of alpha u plus beta v comes out to be this, that is T of alpha x1 beta x2 comma alpha y1 beta y2 alpha z1 plus beta z2. Now which type of mapping is defined? Mapping is defined in the question. T on 3 elements is first element minus second element plus third element, comma twice of first element. That means first element alpha x1 plus beta x2 minus second element, that is alpha y1 plus beta of y2 plus third element, that is plus alpha z1 plus beta z2, comma twice of first element, that is twice of alpha x1 plus beta x2 plus beta of x2. Clear? This on solving gives you, on taking the alpha terms collectively, we have alpha x1 minus alpha y1 plus alpha z1 plus beta times of x2 minus beta y2 plus beta of z2, comma twice of alpha x1 plus twice of beta x2. Right? Now this will gives you, this is equals to alpha times x1 minus y1 plus z1, comma twice of x1 plus beta times x2 minus y2 plus z2, comma twice of beta of x2. Right? We can do like this. I am taking just alpha components and beta components. Now clearly check this. This is what by definition of T defined here, T of x, y, z, that is T of x1, y1, z1 is what? x1 minus y1 plus z1, comma twice of x1. Right? Similarly, T of x2, y2, z2 is what? x2 minus y2 plus z2, comma twice of x2. Beta. Okay? That means this is what? Nothing. This is T of u plus beta T of v. Right? Thus, T is a linear transformation. Okay, students? Okay, hope you can understand easily. Now I am going to discuss a second example. Second example, yes students. Second example on integration, that is also very easy. That means you have to prove TF C to D fx dx, where f belongs to vector space V and C comma D are any scalars belongs to the field F, that is R here. ठीक है? We have to prove T is, to prove T is a linear functional. Linear functional. Proof. First of all, we have to take two elements from the vector space. Here we are talking about functions. That's why I am taking two functions, f and g belongs to V. And I am taking two scalars, alpha and beta belongs to field R. This implies, because V is a vector space, according to definition of vector space, alpha g plus beta f belongs to V. Clear? Now, apply the transformation. T alpha g plus beta f is equals to, according to definition given here, C to D alpha g plus beta f of x dx, which can be easily written like C to D alpha of, we can split this on x, gx plus beta f, that is f over x dx, right? Which can again split the integration C to D alpha gx dx plus beta C to D fx dx, which is what, according to definition, this is what, alpha t of g plus beta t of f. Okay? This implies given t is a linear function. Okay? We can easily check. Now, third example, when we have to show the given mapping is not a linear functional. For example, students, we are given any element x, b1 v1, b2 v2 plus b3 v3, right? And we have, where we all know v1, v2, v3 are the elements of vector space, b1, b2, b3 are scalars, and mapping is given f of x is what? b1 plus 1. This. Check whether this is linear transformation or not. Right? Solution. Now, first of all, we have to check, therefore we have to satisfy or check these two properties. To show this is sufficient, to check we have to satisfy both. If one of them is not satisfied or violated, then this mapping is not a linear transformation. Now, I am taking the homogeneous property. I am taking f of alpha x. F of alpha x is given to you by you. X is this, that is alpha f of alpha b1 v1, alpha b2 v2, alpha b3 v3. Now, according to definition of x, if x, then it gives you the first component scalar plus 1 only, that is f, first component scalar plus 1. This is what? Alpha b1 plus 1. Okay. Now, what is right hand side? Alpha of fx. Now, what is the value of fx? Fx is b1 plus 1, it is alpha b1 plus 1, which is gives you alpha b1 plus alpha. Clearly, f of alpha x from 1 and 2, f of alpha x is not equals to alpha of fx. This violated the homogeneous property. Therefore, this type of mapping f is not a linear transformation. Students, practice the other exercise also. If any doubt, you can anytime contact me. Thank you.